Hello again. My name is Jim Bradley, and I am the faculty sponsor of the College of DuPage Math Club. Today, we're going to have a talk about mathematics, which is a COD Math Club work product, and this talk was given in December of 2021. I shared this with my discrete math class, and so these comments are preamble to Jesse's talk, but primarily for my discrete math class. So things to notice during Jesse's presentation. Mathematicians make conjectures and then try to prove them. Jesse's conjecture was first proposed by Paul Erdős and a collaborator. And as my colleague Jim Meducci says, many Erdős conjectures are out there. Paul Erdős was an influential Hungarian mathematician who in the later part of his life spent a great deal of time writing papers with a large number of collaborators. This is a picture of Paul Erdős. He wrote more papers than anybody else, over 1,500, although Euler published more pages of mathematics, but there were fewer papers, about 800. And he had over 500 collaborators around the world. And he spent his time traveling and working with the collaborators. He was a caregiver for his mother, and so she often traveled with him. The idea of an Erdős number was originally created by mathematician friends as a tribute to his output. Later it gained prominence as a tool to study how mathematicians cooperate to find answers to unsolved problems. And there are several problems that use an Erdős number as a proxy, and they tell how authors cluster and how the number of authors evolves or as new theories propagate. Several studies have shown that the leading mathematicians tend to have particularly low Erdős numbers. The mean Erdős number of a field medalist, the highest honor you can win in mathematics, is 3. Only a little over 7,000 have an Erdős number of 2 or lower. As time passes, the smallest Erdős number can be achieved will necessarily increase because mathematicians with low Erdős numbers die, and that means they become unavailable for collaboration. Still, historical figures have low Erdős numbers. For example, the renowned Indian mathematician Ramanujan, and this was a book about his biography that I would recommend, The Man Who Knew Infinity, has an Erdős number of 3 through his mentor, Hardy, who wrote A Mathematician's Apology, also a very worthwhile reading, even though Erdős was only 7 when Ramanujan died. There is a biography of Erdős that I've recommended to some of my students. The title of this is The Man Who Loved Only Numbers. One of my students, a young woman, told me she thought that was very sad, that he loved only numbers. I told her she didn't appreciate how deep the love story really was. Another thing to notice during the presentation is progress is sometimes achieved a step at a time through special cases. The great mathematician Sophie Germain contributed to Fermat's last theorem, particularly for n equal 5. And Sophie Germain is an interesting story among her to herself as well. She began corresponding with the great mathematician Gauss, but she had to disguise her name, so she wrote to him and signed it like she was a man named Monsieur Leblanc. Gauss was eventually thrilled to find that his pen pal was a very gifted woman. She proved that if x, y, and z are integers, and if x to the fifth plus y to the fifth equals z to the fifth, then either x, y, or z must be divisible by 5. That was a major step towards proving Fermat's last theorem for the case where n equals 5, and the general theorem, which was proved and described in this excellent book as well, Pierre Fermat's last theorem, was not proved until the late 1990s, and what it says is that if x, y, and z and n are integers, then x to the n plus y to the n equals z to the n can be solved for any integer greater than 2. Another thing to notice from Jesse's presentation is that collaboration is very much the norm, not only in Erdős, but with others. Papers are written jointly frequently, and increasingly this happens across diverse mathematical fields. There are Erdős numbers, and Jesse has an opportunity to earn an Erdős number. He studied with a person who has an Erdős number, and they may someday collaborate. And you can see that Jesse, in fact, collaborated on the paper he's talking about with Jack Witt. Another point, the problem need not be motivated by an application, but that does not mean that today's abstract mathematics will not become tomorrow's applied mathematics. This is Lobachevsky, who developed hyperbolic geometry, which proves that Euclid's fifth postulate is interchangeable with other postulates and still have consistent geometry. And he was also a rector of a great Russian university. And in fact, the exact quote is, "There is no branch of mathematics, however abstract, which may not be someday applied to the phenomenon of the real world." A final note is that precise definitions are crucial, and we build upon the theorems of others. But the general proof techniques are the same ones that we've studied in our class. You will see that Jesse and Jack's main result is proved by the method of contradiction. And please be aware that AMATIC also sponsors undergraduate research, such as Jesse's sharing with you, and so there are opportunities there. And as you can see, there's many definitions and concepts in Jesse's abstract. Now we'll move on to the main event. I'm introducing Jesse Hayes Carver. This is what he looks like. And he's being embraced by a friend here, and probably that friend is a student. Jesse is a COD Learning Commons tutoring living legend. He's a remarkable young man. He's fluent in Japanese and martial arts. He's an aficionado of high-performance cars. He fosters collies. That means he has a soul. And he is a passionate mathematician who began in developmental math and, in my estimation, has no ceiling. My colleague and my friend, Jesse. Please take it away, Jesse.
All right. So, as Bradley introduced me, my name is Jesse Hayes Carver. I am a senior academic assistant here in the Learning Commons with tutoring services. I've been studying math a long time, since 2008, my first course with Jim Bradley, and since then I have done many years in many disciplines, whether it was analysis through calculus, whether it was graph theory and discrete, or even more recently, some rigorous algebra and abstract algebra. But today's subject of our talk is a study of quasi-kernels and tournaments. Now, I understand that these terms are probably brand new, perhaps never heard of them other than tournament. And the goal of this is to make the lecture accessible. We're going to walk ourselves up through the basics of graph theory to where we can then start to see a little bit as to how a mathematician may take a problem, may develop an abstraction, may make some measurements on that abstraction. How do you start to play and manipulate as you take things beyond perhaps a visual sense? Nice thing about graph theory is it's pretty obtainable. So this is work that I did as an undergraduate at Illinois State, and my co-author is Walter Jack Witt. He prefers to go by Jack. He couldn't be here today, but that's okay. We're going to take it as it comes. So again, study of quasi-kernels within tournaments. So some of you may have seen this already. This is the Map of Mathematics, a YouTuber. I believe his name is listed there, Dominic William, had put this together. And for many of us, we're only familiar with a very small portion. So the way that this is set up is that on the left-hand side, in purple, we have the pure mathematical disciplines. And on the right-hand side in blue, we have something that's more applied. And within this, we're pretty exposed to, let's say the middle bottom left there with the calculus, the vector calculus, maybe some geometry, trigonometry, but there's many things that lie beyond the scope of the courses taught at College of DuPage. Something that I have played extensively with, number systems. I have played with, of course, the foundation. Some of what we'll talk about today is some set theory, combinatorics, number theory, graph theory. These are going to be the things that we're going to be talking today, study of graph theory. So that will be our focus of that entire map. We're looking at one thing, and even a subset of that. Within graph theory, there's many different structures one can study. So, of course, what is a graph? Well, a graph, often seen as this, is a relationship between vertices and edges. where our vertices are denoted in blue, and we tend to label these either by subscripts as v sub 1, v sub 2, v sub n, or if it's finite and small, we can usually go alphabetical. So for this example, we'll keep it small. So our graph, I have our notation here in blue. We either denote it as G, or we define it G equaling a set of V, the vertex set, and E, capital E, the edge set. So our edges are black, our vertices are blue. So vertices, as I've discussed, these are our blue vertices. They're sometimes referred to as nodes, depending on who's talking. Usually the computer scientists like to look at them in terms of nodes. And we have our edges. You can also think about these as bridges or connections between two objects. Two distinct vertices are related in a way, if and only if they share an edge. So for vertices, a vertex set, we typically do capital V. And when we talk about a specific vertex, that is reserved for lowercase letters. Likewise for edges, if we're going to be discussing an edge set, if we were to collect all of our edges here, we would describe that in a set, and we would denote that by capital E. Little e would be if we were referring to a specific edge, and that edge would be related based on what its terminal vertices are. So this edge here could be denoted as BA or AB, because this is an undirected graph. More on that later. So with vertices, we'd like to describe the relationships. So we would say the two vertices are adjacent if and only if they're connected directly by a single edge. So in this instance, we have X, this squiggly line in graph theory is to say that X is adjacent to B, and we can see that in the graph here, that X and B, our two vertices, are joined by an edge. Then we also discuss the neighborhood of things. So a neighborhood, as the name kind of suggests, this is where graph theory is nice. A lot of the terminology is used in a very visual and natural sense. So neighborhood of a vertex is often denoted capital N for neighborhood of a specific vertex V. If we take X as an example, the neighborhood of X are all the vertices which are adjacent to it. So that set of vertices would be B, A, and Z. Y would not be included in that set because X is not adjacent to Y, not directly by a single edge. I can get there through a path, but it's not directly adjacent to that with a single edge. X is in the neighborhood of X. Often that is left out in the set because you might be dealing with a non-simple graph or just a graph. So if X has an edge to itself, you'd say X is in its own neighborhood because it is joined by an edge. But for purposes of this talk, we'll be looking at simple graphs, and simple graphs do not have loops, meaning there is no edge connecting a vertex to itself. And there are no parallel edges, meaning that between two vertices, if they are adjacent with exactly one edge. There will not be two bridges connecting, say, X to Z, as we have here. Independence is another key that will be relevant to today's talk. An independent vertice set or vertex set is one such that a collection of vertices in that set are not adjacent to one another, taken two at a time. So I would say that a set containing both B and A is not an independent set because I have an edge right here. However, a set containing B and Z would form an independent set as they are not directly connected by an edge. So now that we have some ways to describe relationships between vertices, we should have something numerical. All this has been in terms of set theory. We get to degree. And degree is often, depending on what we're looking at, the delta, capital delta here, of G. This is the total degree of the graph. Or if we're interested in just a specific vertex, we'll do lowercase d and of a specific vertex. So for instance, if we look at this and I go to vertex B, the degree is measured by the number of edges which are incident to it, which are touching it. So B here has a degree of 2, X has a degree of 3, Y a degree of 1, Z a degree of 3. And another concept we'll need for today's lecture is the idea of a subgraph, similar to a subset. Like a subset, you may have some elements in a subset, or given a set, you have some elements. A subset has to contain some of those, maybe not all, but some. The idea is similar for a subgraph. It's described in terms of two sets, a set of vertices and a set of edges. But a subgraph can be obtained through the deletion of edges or the deletion of vertices. So as an example here, if I delete vertex y, I also have to take the edges connected to y, because an edge must join two vertices. I can't have it hanging out there, only attached at one endpoint, not the other. And also if I delete vertex b, I take its edges, resulting in this triangle. And to some graph theorists, this is a cycle. It's called C3, or it's a complete graph on 3 vertices. More on complete graphs to come. So probably wondering, well, why the study of all these things? Graph theory. So some folks like to know the applications. Where is it used? So just to give you a variety of subjects, computer science, they often use this to represent the network of communications, data organization, computational devices, and the flow of computation. As one thing travels from node to node to node, what path does it take? The edges that connect things. Linguistics, I stuck this one in here for Brian back there. Traditionally, syntax and compositional semantics follow tree-based structures. Now, a tree actually forms a graph, and the best way to think of a tree is perhaps as a family tree. You have your parents, you have the children's children, and the children's children's children. And you have a hierarchy, right? And I have to answer to my parents, but my children should answer to me, that there's a structure based on what came before you. And language and syntax happen to follow a similar structure. So this is whose expressive lies in the principle of compositionality, something I just learned about not too long ago. And this is modeled by a hierarchical graph. So this is our idea of the family tree. Chemistry, we've probably seen this before. So graphs are a natural model for the molecule, where our vertices represent the atoms, the edges, the bonds between those atoms. They often use this when they're looking at computational chemistry, where you're trying to represent the possible outcomes of something. You can store it as a graph, and then you can make some observations on that. Sociology, this is probably the more well-known, to measure an actor's prestige. The 7 degrees of separation from Kevin Bacon is a graph theory problem, or the Erdős number to the mathematicians is a graph theory problem. What's the distance from you to Erdős? I'm looking to get a number, I'm not there yet. We can also explore the spread of a rumor, or to model social network analysis, often denoted SNA. And biology. So this is one that I had studied, a couple years ago, applied to the study of connectomes. So something that biologists are trying to do desperately is to have the first map of a brain, just even a mouse brain, something significantly smaller than ours. And the way that they're approaching this is modeling the nervous system, where you take a cluster of nerves, call that an edge, or call vertice a node, and then you look at the connections between those clusters. You draw an edge, and you try to see, is there any pattern? Cycles, does it form a graph? If so, what type of graph? Is it directed? It only goes one way, but not the other. This is a very, very interesting subject. Big money here if you want to go into applied biology, mathematical biology. So with some of the preliminaries, the essentials out of the way, the balance of today's talk, we're going to look at primary or preliminary definitions to what I mentioned before: the study of tournaments, the quasi-kernels that lie within them, and from there, we'll talk about the history of the problem, how Erdős had a known conjecture for this. Look at some partial results for graphs that have been done so far, some more key definitions relevant to today's talk. The conjecture that my co-author and I set out to prove, our findings for what are called hairy tournaments. Again, we'll discuss that shortly. And an outline of the proof, because the total proof of this is about 13 pages long. So I'm just going to give you the basics. All right, so some further definitions. We discussed what a graph is, but now we need to know what a directed graph is, or sometimes referred to as a digraph for short. So it is made up of a set of vertices. We still have our edges, but now each edge is assigned a single direction. So if these were labeled A and B, I would say A goes to B, however, B does not go to A. Our edges now have a unique orientation. So for the remainder of our talk, we will be working explicitly with directed graphs or digraphs. And again, D in this case is going to denote a digraph, and that's our vertex set, and an associated edge set where we have some direction to it. All right, so now sources and sinks. So a source is a vertex which has 0 in degree, meaning that my degrees can now be measured in 2 ways. Before, we just talked about degrees as does an edge touch that vertex or not. Now we're interested in what way does the edge come in contact with the vertex. So here we look at this example and I see I have a single vertex and I have 3 edges leaving it based on the orientation of those edges. So I would say that this has an in degree of 0. There are no edges pointing towards this vertex, but I would say it has an out degree of 3 edges leaving. Similarly, for a sync vertex, out degree 0, everything is attracted to that point. So here is our example. Vertex, 3 edges pointing towards it, 0 pointing away from it. So I have 0 out degree. Information comes in, but I don't send any information. We also need to discuss what is distance in a directed graph. So distance here is measured by the shortest directed path between 2 vertices, where each edge accounts 1 towards the total distance. So for instance, if I talk about the distance from A to B, that's a distance of 1. I can directly get there from an edge. However, if I talk about the distance from B to A, well, that edge only goes one way. So I have to go around. I have to go B to C, C to D, D to A, distance of 3. Now a quasi-kernel. Quasi-kernel deals with distance. So quasi-kernel is going to select some vertices, put them in a set. That set has to be independent. That was something we mentioned earlier. So no 2 vertices pairwise can share an edge. And also, the distance from any element in that set, called the quasi-kernel, to something outside of the set should be at most 2. So what that means is, for instance, looking at this example, I take D to be the quasi-kernel. And I look at D, it's a single vertex, so it must be independent. It's not going to be adjacent to itself. This is a simple graph. So I look at D and everything else should be a distance of at most 2. So A, I get there at 1, B, I get there at 1, C takes a little bit longer. I go D to B, B to C, that's a distance of 2. So I satisfied the conditions. It is both independent and any vertex outside of the set is a distance no more than 2. Now start to bring ourselves up to speed as we build towards our conjecture. So 1974, Schiff et al. And Lavatz proved that every digraph has a quasi-kernel. So we'll be looking at tournaments, a specific type of digraph, directed graph. 1976, just 2 years later, Erdős and Spichelli conjectured that if every vertex of a digraph has positive in degree, so something has to be coming in, then that graph has to have a quasi-kernel of size at most the number of vertices divided by 2, or simply put, that quasi-kernel contains at most half the vertices of the total graph. So far to date, I should have checked to see if any others have snuck in here in the last year, but I don't think they have. This has been verified for several classes of graph. Semi-complete multipartite, don't worry if you don't know what it is. Quasi-transitive, locally semi-complete, and small hairy tournaments. That is the one we'll be discussing today. A few more definitions. So what is a complete graph? A complete graph is one in which every vertice is adjacent to every other vertice. So this is an example, is also known as K5. It's a complete graph on 5 vertices. So we notice that each vertex has 4 edges connecting to each of the other vertices. And likewise, as we make our way around counterclockwise. And a tournament takes a completed graph and assigns direction to each edge. So you almost think about this as you play games. Who plays who and what order as you go around. Everybody eventually plays everybody. But we can cycle around here and see how the interactions between these go. So for our study again, tournaments, complete graph with directed edges. So a digraph. So we're still within the scope of our conjecture. Now a hairy tournament takes a tournament, a complete graph with directed edges, and adds sync vertices. Doesn't have to be to all of them. I left one out on purpose. However, the vertices which make up the tournament part, often referred to as the core of the graph, these will have sync vertices. And the sync vertices, as you notice, are all of in degree. They have no out degree. They take in information, they receive it, but they don't send anything. Only the tournament deals with the transfer of information between things. Once you hit a sync vertex, you're done. It's the end of the transfer of information. So for convenience down here, we have the core part. that I typically do in like this opaque color to kind of give ourselves some structure as to what's going on. So this is a complete graph for the core, K4, complete graph on 4 vertices. And it has several sinc vertices, or hairs as we'll refer to them. So the conjecture is, let G be an n vertex hairy tournament, so a directed complete graph with hair, the sinc vertices. Then there exists a quasi-kernel, K, of the vertex set of the graph, such that the quasi-kernel K has no more than half the number of vertices. Well, we should probably prove some theorems to help us out with that. That's already a big task. So now we start to walk ourselves up. That's the conjecture. The purpose of this talk, we'll look at a specific hairy tournament. It'll have at most 2 vertices, 2 sinc vertices on each of the components which make up the core. All right, so theorem 1, let T be a tournament. For any vertex belonging to the tournament, and this is saying that the out degree of that vertex with respect to the tournament, this is our notation, is the maximum out degree of the tournament, then that vertex V must be a quasi-kernel. Doesn't have to be the. It's one of the possible options that you could collect in a basket of vertices and label a quasi-kernel, but this one has to be one of the possibilities. Let's go through a proof. Take a deep breath, it's not too bad. So first, the setting is any proof. Let T be a tournament, has n vertices and is an integer, where V belongs to the vertex set of the tournament, such that the out degree of V is the maximum out degree in the tournament. Then we're going to say, okay, it's been set. We need to put a value on it. We still have to keep it arbitrary. I don't know if it's 2, 5, 20, or 100. So I'm going to let it be K. Now K has to be somewhere between 0 and n. It has n vertices, it can't connect to itself, so I have strictly less than, and it's not going to be 0, because no matter how you orient a tournament, something is going to have a positive out degree. So I have an inequality here which pays to my advantage in a little bit. All right, so since V is a vertex of maximum out degree for our tournament T, this implies that any other vertex A belonging to the tournament has an out degree at most the one of V. We said that V is the greatest. Anything has to be just as great or less. And we said that's going to be equal to K. I denote this by star. We'll use that in a moment. By way of contradiction, one of the mathematician's favorite tools, suppose V is not a quasi-kernel. So what does it mean to negate the definition? You have to satisfy 2 properties. It's an all or nothing promise. It's and. So either it is not an independent set, or the distance between the vertex V and something else has to be greater than 2, because we said it had to be strictly less than or equal to 2 in order to be a candidate for the quasi-kernel. So, well, it's a single vertex. Has to be independent. Any singleton set of vertices is independent. There's no edge from itself to itself. We're dealing with a simple graph. So we're forced to conclude that there has to exist another vertex A where the distance between V and A is greater than 2, violating the second condition to be a quasi-kernel. Now, since T is a tournament and the distance between V and A with respect to the tournament, that's our notation here, subscript T with respect to the tournament is greater than 2, this implies that V does not have an edge pointing directly to A. That would be distance 1. And we said that can't be the case because it's distance greater than 2. So we're forced to conclude, because again, it is a complete graph, there is a vertex leading from A to V or V to A. It's one of the options. It can't be V to A. The edge must go start at A, end at V. So here's a picture, kind of motivate what's going on here. That's the nice thing about studies of graph theory. When things get too far into the weeds, you can usually pause and illustrate kind of what you're thinking and share that with somebody else. In my case, it was my collaborator, Jack. So here is our vertex V. Notice it's connected, pointing to, adjacent to, K vertices. I just labeled these B1 through BK. Since I claim that its out degree is K, there's the K vertices. And now A is pointing towards V. If I had V pointing towards A, I would have distance 1, I'd have a contradiction. So I have to consider A pointing to V. So how am I going to build a contradiction here? Because our technique here is by way of contradiction. Well, let's see. Since V has an out degree of K, this implies that for each BI we saw in the previous slide, in the vertex set of the tournament, where I ranges from 1 to K, where V is adjacent to BI, points from V to BI, we have A pointing from A to BI. Again, we're trying to make sure we satisfy the conditions that A is a distance greater than 2 from V. Otherwise, if there exists an I in there, let me go back to it after we discuss this. So otherwise, if there exists an I from 1 to K inclusive, such that BI points to A, this would imply a distance of 2. So let's say B4. If I flip the orientation of this edge and B4 pointed from B4 to A, I would go from V to B4 to A. Contradiction. So I am forced that this has to be the structure of the graph. We're looking at all possible cases. However, since A points to V and A points to BI for every I between 1 and K inclusive, this implies that the out degree with respect to our tournament of our vertex A is greater than or equal to K plus 1. Again, we'll go back here. A has an out degree of K, but also of V, adding plus 1. At least there could be other vertices which it's adjacent to. We don't know, but I'm guaranteed at least K plus 1 of them. So therefore, we have a contradiction. I said that the highest out degree of our graph was K. I found a vertex which had K plus 1. Contradiction, I can't have it both ways. So because of that, my assumption must be false, and I have to conclude that V is in fact a quasi-kernel of our graph, of our digraph, which is a tournament T. So now, how to structure it? Why would I have such a result if I didn't need it? Well, now we begin the abstraction part in mathematics. So here I have a randomly selected hairy tournament. Core part is K4, and it has some sinc vertices forming the hairs. What I'm going to do is first I'm going to pick the vertex of highest out degree. My previous theorem just said that's going to be a quasi-kernel, guaranteed. So I'm going to pick it. Having chosen that, I'm going to look at the distance that things are from my selected quasi-kernel. So I label them distance 1, this is distance 2. I begin to structure the graph in such a way that I can abstract it and work with it in a more general sense. So the idea here, everything in the red box forms the hairy tournament. Everything in the blue box is the core, the tournament part, where red is the quasi-kernel. Sometimes that is referred to as the king of the tournament. Graph theorists like to play with the language. So that could be our king of the tournament. And I'm guaranteed everything in layer 1 is distance 1 from the king. Everything in layer 2 is a distance of 2 from the king, and I have the hair sitting off to the side. Here's another interpretation, a little bit larger for us to look at. Given a hairy tournament G, I can break it down as follows. I have the tournament part in blue. I have the hair in this burnt orange color. I separate my layers. Everything in layer 1 is distance 1 from the king of that tournament. Everything in layer 2 is distance 2. And I have to figure out how am I going to pick the right vertices to get my conjecture. Because again, conjecture is take a collection of vertices that forms a quasi-kernel, so independent set, and the distance from anything outside of that set is at most 2 from something inside the set. How am I going to do it? The natural choice is, of course, to pick the king and also to look at the hairs which are attached to layer 2. Because these are a distance of 3. I'd have to go layer 1, distance 1, layer 2, distance 2 to get to these hair, distance 3. All these are already covered by the king, distance 1, distance 2. So I should naturally consider constructing a quasi-kernel of these. And these are all sinc vertices that are connected to things in layer 2. So there is no edge. These are outside the tournament part. There's no edge from the king to those hair, so they're going to be independent. So that's the motivation. but it took some small examples to build up the intuition to abstract it in such a fashion and orientation. So theorem 2, this is the one that we're going to give the outline of today. And I say the total proof of this one in particular is 13 pages. So we're going to take an arbitrary hairy tournament G with n vertices. We're going to take T as a subgraph of G, that's the core, the tournament part. And if, this is the fun notation, I'll read it once and I'll tell you what it is in layman's terms after. If the out degree of V with respect to graph G intersected with the graph as a whole, the vertex set of the graph, throw away the components in the tournament, is less than or equal to 2. What this is saying, look at the out degree of a vertex, any vertex in the graph, in the outside of the tournament part, because we're doing set minus here. Take the graph, throw away the tournament. Look at all the vertices of out degree. We want to ensure that we have at most 2 hairs. So what this is saying is that for vertex V, we want at most 2 hairs for any vertex in the tournament. Then G is guaranteed to have a quasi-kernel within the vertex set of the graph G, such that it contains at most half the number of vertices. So anytime this statement shows up, we're really reading this as the number of hairs. But doing it in formal set theory logic, we have to do it rigorously. This is the rigor. But layman's terms, this is the hair of the tournament. So in essence, our proof. In graph theory, we often do proof by minimum counterexample. So you're going to say, all right, by way of contradiction, suppose this does not exist. Consider the smallest such graph that the deletion of a single vertex or edge brings you to where that conjecture would hold. So maybe it holds for tournaments of size 20 with 50 hairs, but it doesn't work for tournaments of size 20 with 51 hairs. I can delete a single hair and maybe get it to work for something smaller. And we do this based on the number of edges. So through the reduction of edges, I take my original graph G and I look at a subgraph G star where the conjecture holds. Now, since the conjecture holds, I can find this quasi-kernel. Since I'm in G star, I'll label it K star to keep the association. I can find a quasi-kernel K star within the vertices of my subgraph G star. Now the tricky part, this is where the proof got to be quite nasty, is I have to figure out a way to take the set which was guaranteed and somehow manipulate it to go back to the original graph G, hence the modification from K star to get the graph G back and find a quasi-kernel for G. So to give some illustration to this, everything in this box is graph G. Graph G, of course, has its own tournament. In red, I've labeled that the king of that tournament, vertex with highest out degree. And within this, I will look at a subgraph. So of G, I'm going to take G star. And the way I'm going to obtain that is I'm going to take the vertex of highest out degree and remove it. As I said, subgraphs are obtained for the deletion of vertices or edges. I delete this vertex along with all of its edges. And now I have a tournament T star, which is denoted here in blue. It has its own king, V star, also denoted in blue, sitting inside G star. So this is how I had to organize the material to keep it straight in my head. Otherwise, things get too crazy. So if I can start to visualize what's going on, kind of isolate what's important, what's not important, I can focus on what do I need to get the conjecture that I'm after. So this is the abstraction. Very far away from a complete graph with oriented edges with some hair on it. This is what we're looking at. This is our structure. So we have some useful lemmas. These we will not prove here today. They are proved in the paper. That if you take a n vertex tournament and the vertex belonging to that tournament is chosen such that it is of the highest out degree, the maximum or the king as we refer to, then the vertex in question, the king, is connected to at least half of the remaining vertices, is what this is saying. It's not n over 2 because it's not connected to itself. It's n minus 1 over 2. Remove itself, and that's how many it's connected to at least. That tells me how many vertices I can expect in layer 1, things of distance 1. Gives me some information. Lemma 2. I mentioned that we're going to be dealing with minimum counter examples, and that'll follow after this. We'll need this one. So let G be an n vertex hairy tournament. T be a contained graph within G such that it's the core of the tournament part. If for any two distinct vertices, which are not the same in the tournament, we have that the number of hairs on vertex X is equal to the number of hairs on vertex Y. That's what this is saying. And the hairs attached to vertex X and the hairs attached to vertex Y form the empty set, meaning they have no hair in common. We're guaranteed that we can find a quasi-kernel within graph G such that it has at most half the number of vertices of the total graph. So this is the part where we're getting very specific. Now, I mentioned before that we utilize proof by minimum counterexample. Well, we need to discover some properties of what a minimum counterexample has. We said we could think of some, but I want to classify any minimum counterexample. I need to ensure it has some properties, and these also have to be proven, shown in the paper. So let G be a minimum counterexample to our theorem 2, which we just had. And we have the T contained within G, the tournament part, again referred to as the core. Then G satisfies all of the following properties. For any vertex outside of the tournament, the in degree of that vertex is 1. What that is saying is that any hair outside of the tournament has only in degree 1. There's only one edge leading to it, not 2, not 3, exactly 1. Second part, for every vertex in the tournament, the number of hairs attached to that tournament is at least 2. Could be 3, could be 10, but I'm guaranteed no fewer than 2 for any vertex on the tournament part. Now, theorem 2. This is what we are going to give the proof outline of. So let G be an n vertex hairy tournament with a core T, the tournament part. If the number of hairs is no more than 2 for any vertex belonging to the tournament, then G has a quasi-kernel K such that I contain in that quasi-kernel an linearly independent set. Everything outside of that set is a distance of 2 to something in that set, at most 2. Also, I know that the number of vertices in that set is at most half the number of vertices of the graph. So I have an upper bound on these things. So we assume by way of contradiction that this is false. So we let G be a minimum counterexample to this theorem. We just proved some nice properties of minimum counterexamples, or stated without proof. We know that from, that was lemma 3, our properties of minimum counterexamples, that for any vertex outside of the tournament, its in degree is 1. There's only one edge pointing towards it, passing information to it, not 2, not 3, exactly 1. Furthermore, the other nice property of lemma 3, our minimum counterexample, is that for every vertex in the tournament, we know that it has at least 2 hairs. But look at our statement. The if statement still holds. By way of contradiction, we're only negating the conclusion. Well, the if part holds, so I know I have at least, or at most 2 hairs. This part also holds. I have at least 2 hairs. I have to conclude I have exactly 2 hair. It's the only way that that's true. But this combined with our other lemma, lemma 2, I know that each vertex, let me go back to it actually. But to summarize before I bring it up, I know that this will hold because I have the number of hairs for 2 distinct vertices is the same. It's exactly 2. And also, no 2 vertices will share the same hair. It's in degree 1. So only one vertex can point. One vertex in the tournament can point to a single hair. I don't run into the issue that this would be false. So it's subtle, but I did want to highlight that part as to how I can go from this to this, highlighting all of the stuff that we've proven up to that point. So because of this, and our previous lemma, I'm guaranteed that I have a quasi-kernel K that's of size at most half the number of vertices. And of course, QED, right? Our little box. So with that, it concludes the outline of that specific case to the proof. Of course, I'd like to thank you all for your time and attention. Maxwell, thank you for hosting me for the Math Club. Professor Bradley, thank you for inviting me to this and the wonderful opening remarks.